Hello, everyone. My name is Yihao, a postgraduate student at Shandong University. I'm really glad to be here to present my work, zkCross, a novel architecture for cross-chain privacy-preserving auditing. Let's begin with a simple question. Picture this: you usually use PayPal for payments, but when you travel somewhere new, PayPal isn't supported. How do you buy things there? The answer is simple. You need to withdraw your funds in the PayPal to a bank, and then the bank transfers money to a local payment store like Alipay. This example shows that PayPal tools has their specific applications due to factors like location and the demands of different users. Of course, because besides the two mentioned payment tools, there are many others like WeChat Pay and Apple Pay. Each has its own application scenarios, and they cannot interact directly with each other, which we call the isolated island problem. Similarly, blockchain also faces isolated island problem. To be specific, with the development of the blockchain industry and diverse applications, companies, governments, and universities adopt independent blockchain systems with diverse functionalities. As of July 2024, there are over 10,000 active cryptocurrencies listed on CoinMarketCap. Among them, Bitcoin holds the top position with a market capitalization of $1,200. We can get that as blockchain develops, its isolated island problem is become increasingly severe. There exist data barriers among blockchain systems, which hide the free information flows and value transfers, preventing blockchain technology from being full play to their core advantage in providing consensus and trust. Fortunately, cross-chain technology provides an effective solution serving as a bridge for interactions among isolated blockchain systems. As shown on this slide, two independent blockchains can achieve interactions through cross-chain protocols. Currently, there are many cross-chain projects, such as Cosmos, Polkadot, and IntelliJ. Next, we will introduce some background knowledge on cross-chain interaction to help everyone to understand the content of the solution. This slide introduces two types of cross-chain activities: cross-chain transfer and cross-chain exchange. As shown in the left picture, cross-chain transfer refers to the process of moving funds from one blockchain to another. Cross-chain exchange, as shown in the right picture, is the process of exchanging funds between different blockchains. In the implementation, significant technical differences arise due to considerations like atomicity. Current cross-chain protocols can be divided into centralized and decentralized types based on whether a third party is introduced. Centralized schemes such as notary schemes and relay chains need the implementation of a third component to support the interactions among chains. Decentralized schemes refer to those relying on the inherent machines of a chain, without the requirement for additional entities. Decentralized solutions are mostly based on SPV or HTLC. Now, cross-chain solutions still face challenges, especially in the areas of privacy and auditing. Our work addressed three challenges that cross-chain protocols are facing right now. The first challenge is the cross-chain linkability exposure problem. Compromising on linkability can lead to user data leakage. According to IBM, the global average cost of a data breach in 2023 was $4.45 million. We define unlinkability as an adversary is unable to link the receiver's account from the transactions sent by the sender, and vice versa. The second challenge is incompatibility of privacy and auditing. The demands for both privacy protection and auditing often exist in a system, and these two requirements have conflicting goals. To the best of our knowledge, no existing cross-chain work can solve this conflict. The third challenge is for auditing inefficiency. The auditing has long been an important research topic for single blockchains. This problem becomes even more challenging in cross-chain. Specifically, the design promise of a single chain assumes that the auditors serving as blockchain nodes can access information within the chain. However, in a multi-chain scenario breaks this premise, as auditors of one chain cannot obtain all information from another chain. Of course, auditors can register accounts on all chains, but it is impartial for real-world applications. For instance, the ledger size of Bitcoin and Ethereum has reached 500 and 700 GB, respectively, and they continue to grow over time. This indicates that when auditing Bitcoin and Ethereum, an auditor requires at least terabyte-level storage space. And as the number of blockchains in the network grows, the demands also increased. This poses a significant barrier for auditors. As a result, it is hard for single-chain solutions to be inherited in cross-chain. In response, we propose zkCross, which includes 3 techniques to address these 3 challenges. The first technique is privacy-preserving protocol for cross-chain transfers. The entire protocol is divided into 3 steps. First, a user adds points amount on the blockchain. To protect privacy, this amount is fixed denomination. Moreover, we hide user R's address by hashing it. In the second step, S sends some parameters to R for verifying the latency of the first step. This process is executed off-chain. Finally, we design a circuit for R to mint the amount. R can use this circuit and the parameters received from S to generate a zero-knowledge proof, which hides the information of S and proves the correctness of the amount. The second technique is a privacy-preserving protocol for cross-chain exchanges. The entire protocol is divided into 3 steps. First, S needs to generate 2 independent hash logs and convinces R of the correctness of the unlocking information without revealing the. We construct a circuit for S to achieve this. S generates a zero-knowledge proof based on the circuit and sends it to R off-chain. In the second step, both parties use the 2 independent hash logs to log amounts on the blockchain. Finally, S and R generate a zero-knowledge proof to extract the amount, hiding the unlocking information while proving the correctness of the amount. The third technique is an efficient auditing protocol for cross-chain auditing. We construct a circuit for the committer, allowing multiple transaction verifications and audits to be compressed in a single zero-knowledge proof. The entire protocol is divided into 3 steps. First, the committer completes the setup of the zero-knowledge proof, generating the corresponding proving and verification keys. Next, the committers package the transactions to be audited and generates a zero-knowledge proof. Finally, the committer sends the proof to the auditor, who verifies it to complete the audit. We have conducted experiments on zkCross. First, we test runtime of zkSNACK in the cross-chain transfer and exchange protocols. Initialization and proof generation times were in seconds, while verification time was in milliseconds. Since only the verification process is executed on-chain, the on-chain cost is low. For the auditing protocol, we conduct a collaborative experiments on the audit efficiency. One experiment used our protocol and the other did not. The results indicate that when the number of transactions is 10,000, the audit time is around 3.15 hours without our protocol. With our protocol, the audit time decreases to about 40 seconds under the same conditions. In conclusion, we identify three important challenges in cross-chain privacy preserving auditing, namely cross-chain linkability exposure, incapacity of privacy and auditing, and for auditing inefficiency. To overcome these challenges, we propose zkCross, which is a novel two-layer cross-chain architecture equipped with three cross-chain protocols to achieving privacy preserving cross-chain auditing. Among these three protocols, two are privacy preserving cross-chain protocols for transfer and exchange, respectively, and the third one is an effective cross-chain auditing protocol. In our future research, we will focus on enhancing the system's resilience against attack while maintaining privacy. Moreover, we will extend zkCross to support multi-layer auditing, thereby expanding its application scenarios and further optimizing the audit efficiency. That is all my presentation today. Thank you for your listening.